Okay, so chapter 6. We finished with a lot of the probability. We're going to get into a lot of stuff that's probability, but not the same kind as last chapter. So hopefully, for those of you who are struggling a little bit with the normal probability, this will be a little bit easier for you. So, okay, so starting off with vocabulary, just like normal. Okay, random variable. All right, so a random variable. Obviously, it's a variable. Okay, so a random variable, basically you're assigning a numeric value to the outcomes of a chance process. Okay, so let's say like flipping a coin, right? And you are defining flipping a coin and getting heads, sort of like we defined probability variables in the last chapter, where you have to state that X represents flipping a coin and getting heads. Okay, so that's a random variable, and it's a numeric representation of that, so you can actually give it a number answer. Okay, probability distribution we've already seen. This is the same as it was last chapter. Basically, you're going to make, it's basically a probability model. You're going to make a table that has all the possible outcomes and all of their probabilities. Okay, so this is very close to what it was last chapter as far as the definitions. So we have our X, whatever we're going to define our X as far as like what we're looking for as an outcome, and then we're going to make a table from it. But as you can see from the title, and if you looked at chapter 6 already, discrete means that there is a specific number of outcomes, and continuous means it's infinite. Okay, so we're going to be looking at two different kinds of chance outcomes. You're going to see a lot of stuff that's already familiar. And you can pause this video as you go, since everybody's basically watching it at their own pace, and fill in the notes or fill in a Quizlet if you're doing vocabulary. You can go back and replay it if you need to. All right, so discrete random variable, as I stated, discrete means that there's a specific number of outcomes. So imagine a random variable, basically a description, right? You're defining your probability. Imagine it that something that has a set number of outcomes. Flipping a coin has a set number of outcomes. It's heads or tails. Even rolling one die has a finite set of outcomes, 1 through 6. And if you're talking about like some of the dice they use in Dungeons and Dragons, it could be anything up to 20, or even maybe more. Now the sums when rolling 2 dice, we did a probability table for this last chapter, and we saw that the totals or the outcomes were everything from 2 to 12. And that's a discrete or a finite set of outcomes. Okay, so yeah, what we've been looking at so far have all been pretty much discrete random variables. And this is exactly what we saw last chapter. Every outcome and then its corresponding probability. So we're kind of taking probability up to the next step, because we're going to be using our z-table and doing all kinds of other things as far as the questions. And you already know the 2 rules for this. It's the same rules as it was before. Every probability must be between, I hope you said it, 0 and 1. And the sum of all the probabilities has to add up to, I hope you said it, 1. So same rules as last chapter, we're just taking it up a notch. Okay, and again, pause the video wherever you like, however many times, go back and replay, that's fine. Fill in the notes as you go, please. The notes are in Google Classroom. Okay, so we did this one already, and I'm just going to go ahead and fill it in. We should know what these outcomes are from the last chapter. When you're rolling 2 dice, you can get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are your possible outcomes. Slide that that down a little bit. Okay, and then the probabilities, we saw that it had this really nice pattern. There's 1 out of 36 ways to get a 2. Same thing with the 12. 2 out of 36 for the 3 and for the 11. 3 out of 36. 4 out of 36. 5 out of 36. And then the one that is the most common, 6 out of 36. You don't have to reduce these. You don't have to, make them into decimals if you want. Although if we're going to do a histogram of it, decimals will probably be a little bit easier to graph. But we can take this probability model, the probability distribution, and we can make it into a histogram. Okay, where your value, your outcomes, are your x's along your x-axis, and your probability is your y. You can do this in your calculator. You go into your stat plot like we did before. Obviously, you have to put your data, right? You have to go into stat and then edit and put this in L1 and this in L2. And if you type the fractions into L2, even using a division bar instead of having to hit the little alpha y equals to get your fraction bar, the calculator will actually swap it over to a decimal for you. Okay, so we're going to go ahead and make a histogram. So pause it if you need to and type the data into your calculator. And then we're going to go to stat plot so that we can actually put in our values. Okay, so your X list is going to be where you put your values. So this is the first time that we've ever actually did a histogram with 2 sets of data, because normally we just graph 1 set of data. So pay close attention to this, please. In your calculator, your X list is your L1, right? And where it asks for frequency, normally we had just like 1, right? That was all we had because every number counted 1 time. You're going to put L2 for your frequency. Okay, that's where you're going to put your probabilities at. And no, in case anybody is wondering, there's nothing there and there. I just ran out of room to get it in there. Okay, so we're going to make a histogram. So once you get it into stat plot, we normally do that. We normally hit graph, and then we hit what? Zoom 9 to get it to stat window, I believe. Okay, so do you remember when we were doing histograms before, we had to go back and adjust our window a little bit just to make our X scale what it was supposed to be? If you don't remember, when we were doing the histograms before, it was always the range divided by the square root of n. Okay, for a probability distribution, we're going to go by the numbers that we actually have. So you want your lowest X value and your highest X value to be based on your outcomes. Okay, so your X min and your X max. And then our scale is going to be 1 because our outcomes are whole numbers, right? Let's say if our discrete outcomes were like 2, 4, 6, 8, 10, 12, we would want our X scale to be 2 because that's how wide we want the bars on our histogram to be. You could also draw this by hand. It would take you obviously a little bit more time, but you can. So let's go through this. Okay, so everybody hopefully has paused and has put in L1 for our X list and L2 for the frequency, and all the numbers are in there. Okay, so here's the interesting part. Okay, so adjusting the window, you're going to have your X max, okay, needs to be 12. Your X min needs to be 2 because that's your lowest and your highest. Okay, your X scale, as I stated, needs to be 1 because, each of our numbers on our, when we roll a die is considered a, separate outcome, right? So there's not really any overlap. Now, the Y value, okay, the Y value needs to go from 0. It can go to 1, it's fine if you want, but keep in mind that your Y is your probabilities, right? And your probabilities, when you're talking about any kind of a probability distribution, your probabilities are normally not huge, right? Because they all have to add up to 1 anyway, okay? So the easiest way when you do a probability distribution is to go from 0 to 0.5 with a scale of 1, and that kind of makes the window a little bit bigger. So if you want to star that, highlight it, stick it in your notes. Whenever we do a probability distribution, this is usually a good idea for your y values. Okay, so you should see this real pretty symmetric histogram in your notes. Okay, and in your notes, you should be putting in there, like drawing a picture of it. I believe there's an actual place in your notes. Let me see. I've got them up here. It was up here. Where'd it go? Oh, I have your notes up here. I know, because I put them up here to put them into... Oh, how weird. Okay, I had them up here to put them into Canvas or to Google Classroom for you. I wonder where they went. Okay, so, well, no problem. Here we go, note 6-1. Okay, so, yeah, example using the sum of two dice in class. You should be able to draw a nice, what do you want to call it? A nice basic example of what the histogram looks like from your calculator, right there in your notes. You know, so there is some room. And I do have the styluses in class, so if you need a stylus to draw it in your notes, go ahead. Okay, so when you describe it, remember cuss and BS, the center and the, what do you want to call it? The mean and the median are basically going to be the same thing because it is this beautiful symmetric histogram. You know, it should look, and again, this is just a general picture. It should, you know, 1, 2, 3, 4, 5, 6, and then 6, 5, 4, 3, 2, 1. It should be this really pretty symmetric histogram. Okay, and of course, make sure you're stating, you know, with your cuss and BS being specific. You can hit trace in your calculator and then move the arrows left and right, and it'll actually tell you what the numbers are in your bins. You know, since sometimes you can't see the x-axis when you do this, it'll actually tell you what the probability is and what the bin is, you know, what each of your outcomes is as you trace left and right through it. So you should be able to describe the center. Obviously, there's no unusual features. It's perfectly symmetric. I would remember you can't say that it's normal for the shape, but you can say it's either approximately normal or mound-shaped, you know, definitely unimodal, things like that. But make sure you're giving specific statements for the mean and the range. And don't worry about picking out like interquartile range or anything like that. So make sure you're describing that. Okay, so the next part of this, what we can actually do, the calculator will also do some wonderful other things for us. And we can do probabilities from our table that we have, and that's just the decimal equivalents, right? You could add up at least an 8 would be an 8 or more, so that would be from here up, right? You can just add that up, and that's 9, 12, 13, 14, 15 out of 36, which should be, you know, you're close to your decimal if you do 15 out of 36. We can take and do any kinds of probability from a table. But we can also do a lot more calculations, like finding out what the exact mean is, because the calculator will actually do this. The standard deviation, the median, the quartiles, all of that. Okay, so it's not really that much different from what we did before with histograms and data and stuff. Now you just have two lists, right? You have your outcomes and your probabilities to deal with it. So some less than 4 would be not including 4, so it would be just these. So that should be 3 out of 36. And I don't know if I put the answer in that one. Yep, I did. There we go. And again, those are just the decimals. And remember what I said about open response questions? So actually I would get in trouble because this is kind of a naked answer if all I gave was this. I should actually show the fraction that got it. So bad on me. So that would be 3 out of 36. And what did I say for the other one? 9, 12, 15 out of 36 for this one. And again, it's just adding up probabilities from the table. Not too bad of a deal. So nothing new so far other than doing a histogram with more than one set of numbers. Okay, so The mean or expected value, it's actually pretty cool because you have to understand that if I wanted the mean of a data set, I would just add them all together and divide by the number of pieces, right? I mean, you've been doing mean since middle school. But all the pieces aren't worth the same when you're talking about probability, right? If you go back and look at that table, right? 2 is only worth 1 out of 36, whereas 6 is worth more. So it's sort of like assigning weights or values, because that's really what it is. We call it a weighted average. Okay. The other term that you're going to see a lot, and you're going to make sure you want to write this down and remember it, that when you're talking about probability, mean is also called expected value. Okay, so the formula is just a tad bit different. Your calculator will do it quite nicely. You can actually do this with one variable stats, and you do it the same way you did the histogram, where you do your datas in L1 and your frequencies in L2. As long as you have all your probabilities in there, it'll actually do all the work for you. The formula, and this is actually one that's on your formula sheet, and this literally means the sum of all of your probabilities, or all of your outcomes rather, times their outcomes, times their probability rather. Wow, I can't get this straight. All of the outcomes times their probabilities, and you just add them all together. Now, if you had to show work for this on like an open response question, you would show like 2 times 1 out of 36 plus 3 times 2 out of 36 plus, what was the next one? 4 times 3 out of 36. Now, I don't want to write down 11 outcomes. So you have these little ellipses, even that you use in English, and you go all the way in and end, and you go, okay, 11 is 2 out of 36, plus 12 is 1 out of 36. And that would actually be enough work to show what you're actually setting up to find your expected value. Is that you're showing, that you're adding everything from 2 all the way to 12 with their probabilities. Okay, so you can do this the long way, where you literally can multiply them all out and then add them all together. Or you can go ahead and run one variable stats, right, since the data is already in your calculator, and your data should be L1, and your frequency should be L2. And again, it'll run all of that for you. It'll run, mean, all of it, mean, median, quartiles, everything, which is kind of nice because it'll do it just like on regular data. Okay, and it is actually 7. That is the average, which is why, number one, it's also the highest probability, but that's also why in the game of craps, you lose if you throw that after whatever other number you've rolled, because whoever created the game knew the probability that, and remember this is a long term, right? No law of averages, this is a law of large numbers. If you roll 2 dice over and over and over again, thousands and thousands of times, on average, you're going to get a 7 more than anything else. And that's going to be the average of what you roll is going to be 7. Okay? So long-term probability right there. Whoever invented the game knew the probabilities. All right, so let's do one of these. And you can put this in your calculator as well, and it will give you the correct answer, or in your like L1 and L2, or you could do this by hand. We're going to find the average of what you can expect to win if you play the lottery. So for those of you who are already 18, or those of you who are getting ready to turn 18, okay, and this, obviously you can tell this is from a while ago because now you have to pay like $2 for a play for this. Okay, so the lowest jackpot is $12 million, and you have a 1 in 17 million chance of winning. Okay, and I've gone ahead and done that for you. That is 1 in 17 million. Okay, so your chance of losing is 1 minus 0.000. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7, 5, 8, 8, 2, which would be something like 0.99999. 5, 6, 7. What is that? 4. Oh heck, brain fry. 4, 1, 1, 8, something like that. I think 8. Round the 1, 10, round the 1. Yep. Okay. So I think that's what that is. That is your chances of losing. If I got it wrong, You can correct me when you see me next. Just make sure you've got the right number in there. Okay, so if you lose, the state keeps your money. If you win, you obviously get, the $12 million. Okay, so we're going to find the expected value. So probability of winning, 0.0000005882, or 1 in 17 million basically. If you win, you get 12 million. Right? If you lose, so you have to add these together, your chances of losing, 0.99999941118, you lose $1. Okay. If you multiply that out, right, and you actually, do this, basically, this is a long term, right, expected value on average, and here's your long term again. It's like that law of large numbers. What should you expect to basically get? Let's see if I wrote it down. Nope. Okay, I didn't. I think it is supposed to be like, it's either negative 29 or negative 0.59, maybe. So, what does that mean in the long run? You can expect to lose, 29, I was right the first time, 29 cents every time you play. For every dollar you spend, you can expect to lose 29 cents. And that's in the long run. And I'm talking about 29 cents in addition to the dollar you've already spent. So I know that seems rather ridiculous, but that's basically what that means in the long run. Okay. And I know that seems rather weird, but that's what expected value would mean in context. And it's because it comes out negative that it actually means you're losing instead of winning. All right, so standard deviation, you already ran that in the calculator. You saw it'll give you the standard deviation of the dice or anything else. You could put those four numbers into L1 and L2, your outcomes being 12 million and -1, and your probabilities being these two, and put it in the calculator and run one variable stats on it, and not only will it tell you the mean is -0.29, but it'll also tell you the standard deviation. Okay? And the formula, again, is on your formula sheet, and I don't want anybody freaking out when they see it as far as what it means. Remember that we always take the square root when we're doing a standard deviation. So you basically take each piece, subtract the mean, square it, and multiply it by its probability. So it's that weighted thing again where you have to multiply each one by its probability. So again, in your calculator, I would not expect you to run most of these by hand. Okay, and so when you ran the calculator, I don't have my calculator with me, or the number apparently in there, I thought I did, you will get the standard deviation. Now remember what the definition for standard deviation is. It is the average difference from any piece in the data set to the mean. Okay, so if I'm talking about with the dice, the average difference between what you roll and the mean. And remember, we have 1, 2, and 3 standard deviations, just like with any, any set of data that we were doing before. It still works the same way. And I believe with the dice one, 3 standard deviations should take you right out to 2 and 12. Since it is pretty much, it's an approximately normal, it's that nice, pretty symmetric distribution. So 3 standard deviations should take you right out to the 2 and the 12. So, but yeah, and again, the calculator will run this quite nicely, okay, so that you can not have to worry about typing in all those horrible numbers. And I expect you to use your calculator for this. Showing setup like this is fine, and then you get to the end and you do the 12 minus 7 squared times 0.0278, or you can write it as 1 out of 36. And again, this is just showing the setup so that you can prove that you know what it is that you're trying to calculate. All right. So I'm going to give you this one to practice. You're basically going to be finding the mean and the standard deviation. Yes, you're going to be putting it in your calculator, but you're also going to be running a histogram for it. So this will be something that you're going to be putting in your data, or putting rather, actually I think I have this in your notes. Yep, U.S. Census data. It's a nice big practice section right there. Okay, and that's where we're going to stop for today, I believe. But this is what I expect you to do. Confirm the data is discrete by definition of discrete. Okay, so that means that set number of outcomes, right? Okay, set number of outcomes. The data is discrete. And specifically, there's no numbers in between them, right? That you can't have 1.5 people living in a household. Okay, make a histogram, do your custom BS, and determine the mean and the standard deviation in your calculator. So make sure that's all in your notes, and that's where we're going to stop for today. The rest of this section is going to be tomorrow's notes, and I do have a couple homework problems that I want you to look at in addition to finishing this. So we'll call this your classwork, and we'll call this your homework, and this should take you to the end of, no, not to the end, sorry, we have, oh boy, no, we have several more things that we have to do in 6.1 because we're going to be doing continuous. So I want you to read about continuous tomorrow, or for tomorrow for the notes. But yeah, 1, 3, 5, 9, and finish up this one problem, please. Okay, and then again, the notes for tomorrow will be posted in there, or not the notes for tomorrow, the video for tomorrow, the notes are still in there. Take it easy, have a good afternoon, and being that you have this much time left in class, depending on how much you've paused the video, you should be able to get all this plus these 4 problems done before you leave. So there should not be any issues with the homework. All right, behave yourselves.